Hello and welcome to LOS 120. LOS 120. It is Module 5, Chapter 5, and this time we're going to look at regression, one of my favorite areas of statistics. So be ready. And did you notice the first four modules that up here I had model, and I always called it module. It's supposed to be module, but I had spelled it model. And I can say that I was just trying to test you, but I just caught it myself. So that's good editing there, Paul. So we're going to look at regression and regression lines. You can see by this GIF over here that we're going to be doing the best line through the points. Last time we were doing the Excel charts and showing how to plot and how to make a scatter plot. But we're going to look at how we can use that scatter plot to give us more information. So here we go. So the first thing we're going to look at is to see what we're going to be doing. So look, I spelled module correctly there and didn't call it model. But we're going to use a regression line to predict values of a response variable and interpret the slope and intercept of a regression line. So this goes way back to when you were doing y equals mx plus b. We're going to be use that as our model, and that's MODEL. So we're going to use that for our purposes here. But we're going to predict values, and that's the whole idea of stats, is to make predictions based on hard facts and how well we can defend those predictions. And we're going to look at what it means by least squares regression lines, and we're going to find the equation. That's going to be very important. So finding the equation is big. And then we're going to look at how we can make this equation by, you can use calculators. I'm going to use Excel on the computer. And based on the properties, we're going to judge its usefulness. Okay, that's what I just said, is how well can we use this equation and then make predictions from it. And then we'll consider the impact of extrapolation. Remember that little word? Maybe you took a science class and you had to draw graphs and you had to extrapolate that goes beyond the length of the line that you usually graph. That's what extrapolation is. So we're going to use that in stats as well. And then we're going to talk about correlation causation. If there's one thing that you'll know from this class is that correlation does not mean causation, and the limits of all of this stuff. Okay, so those are the bullet items that we're going to look at. So let's look at regression lines. So I'm going to go to the textbook and show you what you should be looking at. So what we just did was basically this over here. And now I'm going to go to the next section of this chapter. This is chapter 5, and just tells us what regression lines are all about. So let's go back to our sheet here. And as I said, the early days of algebra, you had to use y equals mx plus b. Y was the response variable, and the m was the slope, x was the explanatory variable, and b was the y-intercept. That's the point at which the line that we draw goes through the y-axis. That's the basic equation we're going to be using for this particular chapter. You might see it as y equals b plus mx, and also the book has it using other types of variable letters, and we'll get to that in a second. So the best thing to do is to see what we can make out of this information, and to use Excel to come up with a graph that looks like that. See, that has a graph, it has a line. So we're going to make that. So this is example 5.1, and example 5.1 looks like that. So you can say, well, how'd you get that? So this is how I got example 5.1. What I did is I copied. Again, it's easier when you can copy the data. And by the way, this is about fidgeting. Does fidgeting keep you slim? All right, so you can read more extensive here, but it says some people have a lot of tics, have nervousness, or their legs are always shaking. I've been known to have that, and it's just normal. At least that's what they told me. And so there's the fat gain change, and this is the net energy, the NEA. Let me find the NEA here so I don't make it up. And this is the non-exercise activity. So this is like you're not lifting weights, you're not running. It's just the fact that you're burning up calories in everyday living. So that's the NEA change in calories. And you can see the data there. And then the fat gain in kilograms. So we're using the metric system here. Remember, 2.2 kilograms is about a pound. Remember that from your physics days? You didn't take physics, you missed a lot. So all I do is I copy and paste, and it isn't always perfect because for some reason those three numbers don't get copied. You press copy, and I went into this, and I pressed on the first cell, and I added the three numbers that were missing. But this is what you get for your data, and it's by rows. It doesn't matter if it's rows or columns. You're going to be doing the same thing. So what I'm going to do here is just copy this data over again, and I'm going to press the right-click button, press copy, and then I'm going to pick another page, and see the plus button. I'm at the bottom of the sheet next to sheet 1, and I'm just going to add another sheet. And so press that, put that in there, and I'm going to right-click so I can paste my data and apparently what I did, this is real time. What I did, folks, was I messed up. So let me do this again. I'm going to copy, and I'm going to go to the sheet 2 and paste. Now I can paste it. Okay, so now I have it there. So let's see what they want us to do. So over here, they say make a scatter plot of the data and examine the pattern. So I'm going to make a scatter plot here. So let's go back to the beginning. By the way, if you have ever get to mistakenly go to the bottom, just press A1 in this corner cell here and press enter, and you'll get back to that. This is A1. It'll be pretty easy. So I'm going to make a, let me make that bigger. So I'm going to make a scatter plot. So this is from module 4. So insert, and there it is there. And I'm going to make this over here, and I'm going to make it a little bit bigger because I want to make it bigger. So just extend both sides, and there's the plot. So if you're looking at the problem, example 5.1, then what they want us to do is to just see if it's linear, and so if it's linear, use correlation to measure its strength. So let's find the correlation. Again, correlation, if you recall, correlation is, I'm writing this in, then I'm going to put an equal sign here. I'm just entering an equals, and bang, now I get a whole list of different types of functions. If they don't appear, go to more functions there. But I do have correlation already done. So the correlation is between two variables, so I have to fill both of these arrays. So I'll press this up arrow, and I'm going to correlate this set of data. Make sure it's just the data, not the label. And then I'm going to correlate it to the other piece of data. That's the fat gain, just that. And then when I'm done with that, I press this button, press OK. So I have a negative correlation of negative 0.77856. That's not bad. That's like, if you rounded it off, 0.79. So that's pretty good. So we have a correlation of negative 0.79. So that means if we drew a line, that would go backwards. I'm sorry, we'd go negative direction, not backwards. That was silly. Just teasing you. So let's see what else we have to do here. If it's linear, use correlation to measure its strength. So we're going to draw a line. Now, I sort of alluded to this last time, but I'm going to do it for sure this time. But the first thing I'm going to do is I'm pressing the chart area, and I press the plus sign, and I'm going to add axis titles, because that's important. So this axis titles here will be the fat change. If I can get this out of the way here. I just want to, okay, I'll just do it this way. This is a fat gain. And I press enter, and that'll move me to the second line. So I have to press enter my units. And remember, if I don't like the way that looks, and I don't, I want to rotate it all to make it horizontal. I like it that way better. Again, if you go to the right, it says Format, Axis Title. You press this little icon here, and you get your text direction right there. Okay, let's set the axis title for the NEA change. And those units are calories. There we go. So now we have our units. Okay, looks pretty so far. Now, the next thing is we're going to add our line. So I'm going to go in the chart area again. Let me get rid of this thing here so I can see my plus sign. It gives me a whole mess of things that we can do. So the chart, it says trend line. So I'm going to add a trend line. All I do is I press that, and look at that. I have a trend line going in the negative direction here. All I did was go to the plus, chart elements, down at the bottom says trend line. So now I've added a trend line. You'll see there's an arrow here that tells you that there are more options. We'll wait for that in a little bit here. So now you've drawn the best line. This is your regression line. This is how you draw a regression line. So you can say that there's a negative correlation and that we have a negative line. Back in the old Ice Age days, when I was in your shoes, we had to do this by hand. Anyone older than me will probably say this is the way we always did it. But anyone younger, you probably were able to use some type of a calculator, a special scientific calculator, graphing calculator. But this is the easiest way to do it, and it's more accurate. So this is the best line that we can draw that will keep these points as close as they can to this line. Let's see where I'm going to press save, by the way. So now I'm going to go back to what we have to do. Draw a regression line on the scatter to predict the fat change and fat gain from the change in the NEA. So their correlation, remember down the correlation, they may do it a little bit differently. They had negative 7786 and 0.7786. We had 0.778. They rounded off. So we had the same thing, because sometimes you'll see the answer is a little bit different if you follow and do their examples, because they may use a different type of algorithm, a different type of program. So as you can see, this is the regression line, as I mentioned, and I'll show you, by the way, you can change the way this regression line looks. You can make it darker, you can make it colored, you can make it all different ways. And this is the predictive fat gain for a subject with NEA of 400 calories. So if someone has 400 calories, let's go back to our graph, because I like it better. And let's say 400 calories right here. See the plot area down at the bottom, 400 calories, we move up, we hit the line, and then we go across. So the net gain would be about 2 point something kilograms. That would be if we had a net change of 400 calories. So it would be a net gain, a fat gain of 2 point something calories, maybe about 2.2. Let's see what they say. They say, well, they don't really tell us what it is, but it's the same thing. So we just did that. So that's how you make a regression line. And then make sure you read the conclusion, because that's what you'll have to do yourself. So let's go back to our outline. And I did the 5.1 there. I copied. Remember, you can copy and paste it right into a document and pass that in. So this is the best way to show that we have a line, the best line. This is our regression line. And folks, that was the name of our chapter, regression. It's the name of our module 2, or model 5 if you want to do that. Okay, so that's how we did that. And I explained it. So now we're going to find the example of the line shown in our graph of example 5.1. Now we're going to find the equation. So let me go down here. See the review of straight lines first? It says y equals a plus bx. So if you've been used to y equals mx plus b, this y is normal. This b happens to be the m, our m, and that's the slope. They call the slope x, b, and then times x, which is what we have. And then their a is their y-intercept, the intercept on the y-axis. We call it b. So if you want to go there, that's fine. I didn't copy it. I just like to use y equals mx plus b. So using the regression line. So what we need is an equation for this line. So now we're going to go back to this particular line. And remember I said in the trend line, you have some options. So now I'm going to this, the chart elements here on the right. And I'm going to press this arrow to the right. And it says more options. So more options. It says display equation on the chart. I'm going to press that. And there's the equation. Best thing to do is to move it up. Okay, and there's the equation of the line. And so now it's in the y equals mx plus b form. So we know that y, our response variable, that's the fat gain, equals, this is the slope of this line, m, that's the m. It's negative 0.0034, not much of a slope here, but that's our m, times x, which is our NEA change, plus the y-intercept, which is positive 3.5051. You can see it's right there. That goes through the y-intercept. The y-intercept is where 0, 0 is. You go up the y-axis, and that's 3.5051. So that's the equation we're going to use. So y equals negative 0.34x, which is the NEA change, and we're going to see the fat gain. So remember when they asked if you have 400 calorie for x, we're going to just plug it in here and find our y. So let's see if I can do this in a convenient way. I'm going to copy this, Control C, and you can always you can put it in your calculator if you want, or let's see if I can just put it in there and see what happens if I put V. Oh, cool. So I just pasted it right in Google, and I haven't done, this is from an old calculation here, but I'm going to put 400, so it has to be times 400 calories, and let's see what happens when I press enter. So I get, what is it, not even giving me, here's my problem, solution, that's what I want, solution, there it is, right there, the 2.14. Remember when we went on our graph and we said this is 400, we went up here, and 2.14, so I had said it was about 2.2, so I was a little bit off. So this answer on the is 2.1451. You can use your calculator for that. They just did the problem out like that. And so that means that if you have 400 calories of NEA, let's go back to this, 400 calories of the NEA change right here, then that means that you would have about 2.1 kilogram fat gain. And that's how you find it. So again, use the calculated equation right here. You didn't have to do it. You didn't have to find the slope and so on and do anything like that. Let Excel do it for you. And as I said before, Google Sheets can do this. It's just a different type of setup. You can look it up online if you want to. It would just make this video about twice as long if I went and showed you how to do it on Google Sheets. But you can go on YouTube and find them, so be my guest. By the way, if you wanted this line, you can just put the arrowhead right there, and you can format the trend line to any way you want, and you can add color. Remember, it's a linear line. You can do all sorts of things with it if you want to, and you can customize it and so on. So let's see what else you can do. You can shadow it and things like that. So that's up to you. But this is fine. I'm saving it right now. So let's go back to our sheet. And so we did this here. We did this here. So this is finding the example of the line shown on a graph. So now with people with larger increase in NEA, blah, blah, blah. So we're using the fat labels. I've done this. So what I just did is the example here in blue. 2.15 kilograms right there. Ta-da! There it is, your ta-da moment. So be proud of it. Okay, so now we're going to look at the problem 5.1 on page 127. Problem 5.1. Problems are in purple. Did you notice my color scheme? Pretty clever. I thought you'd like that. I'm still mad at myself for that model thing. So the least squares regression line we talked about. So you know in section 5.2, now we have the equation. By the way, skip this. Yeah, this will probably, if you've not done anything like this before, then don't look at this. Okay, the equation of least squares. This uses the y hat equals a plus bx. It's just going to be confusing. Let Excel find the equation for you. This is to solve it. If you do a problem, they'll say solve it by hand or solve it by calculator, and you do this. That's just going to be more of a pain, more of a confusion. And so you can see software, your calculator will give you the slope. Let Excel find you the equation of the line. So there's some examples of technology here. And you can see they have a different type of formula. There's Excel right there. They use a different type of format and way of doing it. The way I showed you is my way. If you want to be really, if you want to take a chance and try to doing it different ways, then be my guest. So we're going to go back to problem 5.1 on page 127. So that's what I was really getting at. So I sort of went back by it. And I'm going to go back to 127. And here's 5.1 here. And missed it. Maybe it's because it's on the other page. Okay, 5.1. Dun, 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 dun. All right, city mileage, highway mileage, and so on. So I'm going to go and show you problem 5.1. So it's very small. You just have 2 points. Remember, you can make a line with just 2 points. That's algebra from 8th or 9th grade. Whenever you took it, you know you had to take it. If you went through a high school or homeschooling or lived in a cave, you had to do it. So it says here, we expect the car's highway gas mileage to be related to its city gas mileage. So they have this equation. Think of y equals mx plus b. So y is your highway mile per gallon equals mx. M is your slope times x, which is your city mileage. That's your explanatory variable. Plus 8.720 is your y-intercept. So they have a little bit backwards here because they like to use that weird equation. But we're going to just look at it as y equals mx plus b. What is the slope of this line? So the slope of this line is right there. That's the slope, 0.914. That's a pretty high, that's almost pretty straight because our slope of 1 is straight 45 degrees. Okay, so it's like a 1-to-1 ratio between the city mileage and the highway mileage. What is the intercept? 8.720. That means that even at zero, if you start the car, they're saying that means that you've already gone 8.72 miles per gallon. You've used 8.72 on the highway. That means you start there. Find the predicted highway mileage for a car that gets 16 miles per gallon in the city, and do the same for a car with a city of 28 miles per gallon. So what I did is and then it's a draw graph. So here is the numbers over here. So I plugged in for 16 miles per hour. By the way, I used this equation, and I went to some Google site, just plugged it in here because I'm too lazy to take out my calculator. Plus, if I take out my calculator, you can't see me doing the problem. So you do it over here. So here are the resulting values. So for city at 16, I get 23.344 miles per gallon. For city at 828 miles per gallon, then you get 34 miles per gallon, 34 plus. So here are my 2 points. So all I did was I highlighted, and you can just highlight the numbers, by the way. And then you go into insert, and then you go into the charts here, and you go to scatter, and it looks like that. Okay, so you press that. That's what I did, and then I fixed the chart title. Okay, you can see you press anywhere here, not in the grid, but out of the grid, and you get those. So I pressed that. I wanted access titles, and you can see that when I press my access titles and I go to this option over here, it's horizontal. Then I put my city over here. Okay, and you always put your explanatory explanatory on the x-axis, and the result or the response variable on the y-axis. Okay, and then I wanted to find the line. So what I did is I pressed this, I pressed the plus sign, and I pressed trend line, and I wanted the trend line. So I pressed that, I got the trend line, and then I pressed more options, and here's the equation down at the bottom. Let me get the equation here down at the bottom. By the way, it's this third one with it looks like a bar graph. You can just keep playing with these things till it shows up. So you want the equation, display the equation. I already did that there on a chart. It's going to show up twice, so I'm going to take that out so it doesn't show up twice. And so there it is. There's the equation of that. Now, it's a little bit different than what they gave us in the book over here. It's a little bit different because it uses the algorithm of Excel. So don't be worried about that. And then what I did, by the way, is to extend the line. So when I draw the line, it only shows up over here. but I'm going to show you that you can go backwards. So if you look at forecast and backwards here, and this is one thing you have to play with a little bit. So how many, and I'm going to just move this over so you can see how many periods. Don't worry about what that means, but if it's like 10 periods and then you press enter, see, it moved it back. And if you want it to go all the way there, you can just keep going. 20 periods, moved it back. So now it's gone back there, but that's okay. So now you know your y-intercept. You remember your y-intercept was 14.28, so it's going through 14.28. So now you can look and say, okay, when a car goes 10 miles per gallon, it probably will go about 23 miles per gallon on the highway. That's what you can do by extending the trend line backwards or forwards if you want. So that will help in extrapolation. And so let's go back to the problem itself and find the predicted mileage. That gets draw a graph. And if a city between 10 and 15 miles per gallon, be sure the scales, axes, and so on. So you can go between 10 and 50. So the problem with doing 50 here is that we're going to be further away. So if I wanted to do the same thing, I can go here and my trend line, press the options, and then go here. And then let's move it forward. Let's say about 20. What happens? Okay, we're still not at 50. If you see, we're not at 50. So let's do another 30. Let's see what happens when we press 30. Okay, now we're at 50. So now we've extended the line. The danger is that you may have to, remember our original data included these 2 points, but we've extended it way beyond the 50 here. So if a car goes 50, it may get about 58 miles per gallon on the highway. If it does 50 city, 58 corner. But you never know that this may drop off because we don't have any data. So when you're doing your research, you have to be careful that you're not extending way beyond the data. And so you'd have to defend this. If you say, okay, a car goes 50 miles per gallon in the city, it will get about 58 miles per gallon on the highway. That's something that you'd have to defend, and it's hard to defend when your points, you only have 2 points and they're over here. So that's one of the drawbacks to extrapolation, just letting you know so you don't get too crazy with extrapolation. So that's what that is. And this over here looks different because that is the answer from the book. So you can look at that and compare. Now, other examples from the next chapter, the next section of the chapter was other examples of technology. The line we have on Excel is called the least regression line. It's the line of best fit. Okay, you might have heard that term. And if you don't believe what I've just said, this is what a least squares regression line comes from, a Google definition. It's the procedure that fits the line to the data points in a way that minimizes the sum of the squared vertical distances between the line and the points. It's known as line as the best fit. So let's look at what it said, that thing I had right at the beginning. You can see these points over here and how far they are. What you do is you take the square of these distances, and that's what the Excel program does. That's what equations do. They minimize these distances here. So that's called a regression. You're regressing towards this line. That's what that whole section means. So it's not something you have to memorize. It's just something you have to be able to understand. So let's look at some similar problems, and we'll look at problem 5.4. So problem 5.4 in the book. Hopefully I can find that much more easily than I just did this one. And I'm going to just scroll down, 5.4. Now you know what you can skip on that. Examples of technology. If you have Excel, you're fine. If you want to use math, you can use a calculator, or you can use your Excel as well. So let's see. We have 5.4 right here. Remember the coral reefs from example 4.2 and 4.10. So this is 5.4. So I just copied the information. This was the original information from that problem. You can look it up. And what they want us to do, went too far, is use a calculator to find the mean and standard deviation. I didn't use a calculator. I use Excel. Remember how to use the mean? You just highlight, you just put an equal sign in this box, and you find the average. There's the average up there. Follow my cursor. There's the equation. And I found the average of the surface temperature. So you just highlight these over here. If you're not familiar, remember, go back to the second module or model. And then the mean of the growth, same thing, is this row over here. Standard deviation, if you look at, we have STDEV.P, standard deviation of population, and we just highlight those. And then the standard deviation of the growth, you just highlight these. So this should be familiar. Hopefully you remember how to do that. If not, you can review that particular video. And correlation, just did the correlation earlier and today with the preceding problem. So that's just a correlation between these two sets of values. And that's a negative 0.8. So that's pretty strong. It's a pretty strong correlation. And then you make a graph. So you highlight, don't highlight the labels, and then you just highlight the data, and you insert a graph like this. In fact, I'll highlight the data, and you can see where the graph comes from. Now I highlight it, insert, and press this, and there's an example right on top of the other example, and you can see all of these other types of charts. So I'm not going to do it because I already did it. Then you make sure you have a clean and clear title. Make sure you have a clear and clean y-axis label and units. The label is mean coral growth. The units are centimeters per year. X-axis surface temperature is your label. Celsius is the degree that we're talking about, so we know the units. And then I went over here and I added the plus sign, and I was able to find the trend line, which I already did. You can see the trend line here going down. And then when I did trend line, I went to more options, and I got to display the equation. It's already displayed up here, and so you don't have to do it again. So this is y, which is the mean coral growth, equals the slope of this line, which is negative 0.1579, times the surface temperature plus the y-intercept. So it would start at 5.039, way up there. Okay, so that's what this equation comes out to be. So when we do all this, they will tell you to do it, enter it on your calculator, say in words what the numerical value of the slope tells you. We just did that. So there you go. Done. Did it before, and that's not what I'm looking for. It's looking this. So I'm going to save that because I think it's pretty. Although you may find that you want to paint this. See this paintbrush here? Go ahead and change the chart styles. As long as it's easy to see. Remember, I'm very old, so I can't always see things. So that was that particular problem. And so the slope, as I just told you, the equation of the line. And now problem 5.5, I copied and pasted it on here. So problem 5.5 should be familiar because we did that in an earlier module. And that's the homicide and suicide rates from counties in Ohio. And so they're asking you, A, make a scatter plot, and find the correlation, and then find the least squares regression line. And what does that mean? And then if another Ohio has a homicide rate of 8.0, what is the county's predicted suicide rate? So let's look at that particular one. That's problem 5.5. So all I did was take the one I did from the previous example and copied it. So this is these are my data here. They wanted a chart, so you just highlight the numbers, go to insert, go to this particular area, and do the scatter plot there. So that's what I did. I made sure that I had a appropriate title. I'm sure I had the title of the label of the y-axis and the units. Same thing here on the x-axis here. So this is the particular example here. Let's see what else they want us to do. They want to find the correlation. So the correlation, I'm going to do that here because I didn't do it yet. So I'm going to write correlation is, so I'll know exactly, and I move my cursor over. I'm going to make this a little bit bigger. And I put the equal sign. Bang. Oh, I already have correlation showing up. So first array. So press that, the first array, no labels. And then second array will be the suicide rate, no labels. And hopefully we get the same correlation as they told us that they got. And what did they get in the book? They said it was negative 0.00645. So this is a weak linear relation of correlation. I do not know why it's so weak. We have a positive one. You can see the points going up there. So I'm satisfied with what we've done. Sometimes the book is different, but this is what we have because we've done nothing different. I would have to check the data, but this is what we did in the first time we talked about that. So follow my cue here. So it is very weak. It's just all over the place. And if we want to, we can say it's funny because they say the homicide rate of 8.0 per 100,000. So I'm going to add a line. So I'm going to press this, add the plus sign, trend line. Yeah, I want the line. And I'm going to add the equation. So let's add the equation. And display equation is right there. Now I'm going to get rid of this because it's cluttering. And I have that here. So there's the equation. And I'm going to copy this. I'm pressing Control C. And I'm going to put it into this particular here, Control V. And I'm going to answer their question. They said in the book on page 131, another Ohio County is a homicide rate of 8.0 and 8 per 100,000. What is the country's predicted suicide rate? So if we look at our chart, and this is the homicide rate, where's the suicide rate? So they said if it's 8.0 over here, you can see, I want to make sure we're on the same right, it has a homicide rate of 8.0. So that means we go to the 8 over here and go to the line, not where the point is. And if it's 8.0, then it would be 14 something over there. But now we're going to find the exact rate. So I'm going to go back to the equation, and this was the 8.0. So this means times, I'm going to get rid of that x because I'm going to replace it with 8.0, which is just 8.0. And let's see what we get. It does the problem for us. We get 14.946 right there, 14.946. I'm at the bottom. Let me bring it up so you can see it. Right there, 14.946 is our answer. So that's that solution. That means that the suicide rate of a homicide rate of 8.0 is about 14.9, almost 15. And we can see that in the chart over here. When you go to 8, it's almost 15, almost in the middle of that. That's what you do. That's how you solve these problems. And so far, I hope that it makes sense for you. So, then some least squared regression. You always need an explanatory and response variables to have a regression line. Remember, you're making linear lines. If you don't have numbers for explanatory, the x, and response, the y, then you can't do this. Least squares regression makes the distance of the data points from the line small only in the y direction. Don't worry about that. As I told you, it just shows you that, and remember, okay, I'll go back here to this graph over here. The least squares means that they take the distance. Look at that. We're going in the y direction. Bang. So whatever that distance is, they square it. And then they square the distance. And then the least squares, there's a long, complicated equation. See how close these are? This is a very small distance along the y-axis. So these are the values that change the direction of this line. So that's what that particular section is telling us. So let's go back to, I want my sheet, sorry. So the correlation R describes the strength of a straight line relationship. In the regression setting, this description takes a specific form, the square of the correlation. Something new. The square of the correlation, R squared, is the fraction of the variation in the values explained by the least squares regression on y-axis. The reason why I'm going blah, blah, blah is because, in other words, this is me now. R squared shows how well the data fit the regression model, the goodness of fit. So from problem 5.1, we can find the R squared to be 0.60061. Let's go back to problem 5.1. There it is there. And now, do you remember that I put the plus sign in trend line options? It says display equation on there. I'm going to go down. Display the R squared value on the chart. Bang. It displayed it on the chart. I'm going to bring it up. It says r squared equals 1. I probably, I don't know why it's, let me do that again. That's going to be the r squared, and set the, did I mess things up? No, I shouldn't have. The r squared value shouldn't be 1 here, because if it was 1, it would be a perfect 45-degree angle. And so let me do this again. And I think it's because I went backwards. And r squared value is 1. I don't like that. So I'm going to go to another one here. Not that one. And let's see the suicide rate. Okay, let's try this one here. I'm going to go back to this plus sign because I want to show you the trend line. I already have the trend line and more options. Come on, baby, don't mess me up over here. Display the r squared value. Phew, okay. All right, the r squared value. What the heck does that mean, Caron? Why do we have to do that? This means how many of these points can be explained. What's the percentage of points can be explained by this line? R squared is your correlation squared, and it's 0.5461 here. So 0.54, this, if you move the decimal place over, you get 54.61%. Remember, percent, you move the decimal point 2 places to the right. This means that over 54% of the points in this graph can be explained by this line. This line includes 54% of the points. That's not bad. But that means also that the other remaining 46% are not explained by the points. So that gives you more strength or weakness in making your final decision. So if we find, let's see if we find something here in r squared. Let's find the r squared value, trend line, arrow, more options. Display equation, already have that. Display the r squared. This is what I have in my example. There's the r squared right there. 0.6061. Move the decimal point over to 60%, almost 61%. So 61% of the line of the points can be explained by the line. So this line is good for 61% of the points. The other 39, too far away. They're not. It could be just variations. It could be just chance. So we're going to be leading into probabilities and so on. So this is why showing the strength of your line. If your line is including 61% of your points, that's not too bad. So the higher the number, obviously, the better. If you had a 1-to-1 correlation, which is why I'm confused as to why I get a 1.1 correlation here, I'm not sure why it came out to 1. It shouldn't, then that means that it's something wrong over there with the whatever I did. But right here in this bullet, we can find r squared to be 0.6061. That means over 60% of the points in our data can be explained by the line. The other 39% is individual variation, can't explain by the line. So your line is about 60% strong. It says, remember this. Guess what? You're going to have to say that in your own words. So the rest of the chapter has a lot of other sections. You can look at it. This is basically what you need for this particular chapter. Here are some things to be aware of. Correlation regression lines describe only linear relationships. All of these over here, this, are all lines. Okay? Nothing else, nothing more. So you can do calculations for any relationship between two quantitative. You can't compare ages of men and women and put boys or girls on the x-axis, right? It has to be numbers. They're only useful if the scatter plot shows a linear pattern. If there's no linear pattern, if you don't have any type of correlation, then it's not going to work. That's why you should do correlation first. The correlation least squares regression lines have not resistance. That means your plot can, when you plot your data, your outliers can really make a difference. So watch out for those outliers. Extrapolation, we just did extrapolation. You can extend your line beyond the data. But remember, such predictions are not often accurate because they can be off your line, and these straight lines may curve up or down or all over the place. So that's why you'd have to defend your choice of making extrapolation. A lurking variable, that's that outlier. It may influence the interpretation of your relationships among the variables. And just because you have a strong association between two variables, you can't draw conclusions about cause and effect. Remember, correlation does not mean causation. It's just one way of looking at things. In fact, researchers would look to see if there's a linear relationship and say, okay, bang, that's the starting point. You're only at the starting point. You're not at the final decision point. So remember that. You're going to be asked if, because of the straight line, if this proves anything or this causes anything. And don't give me the answer that yes, because then that means I wasted a lot of breath, and I don't have a lot of breath left in my life. Final, important concepts. A regression line is a straight line. We already said that. You can use a regression line to predict the value of y for any value of x if you know the equation. Done that before. The slope of the rate is the rate at which y changes along the line of the explanatory variable. So slope is just how steep your line is. And it's usually between -1 and 1. And the intercept is where the starting point is on the explanatory variable. I mean, when the explanatory variable is 0, there's really nothing much to say about that. Like, remember the miles per gallon with the intercept B was around 8 miles per gallon. That's, if you want to go back and say, okay, does that mean when your car is doing nothing, if you had 0 miles a gallon, you're going to get 8 in the highway? No, it doesn't mean anything. It's just a starting point. The most common method of fitting a line to a scatter plot is the least squares, and that's what the Excel does. So you can just use Excel. Please use Excel. And other types of bullets here. The bullets here, the least squares regression line depends on the choice of explanatory response variables. Choose wisely. One causes the other. I mean, one correlates to the other. Does one cause the other? That's how I should say it. Correlation and regression are closely connected. So if you see a correlation that's high, then that means your line is probably going to be good. Look at R squared. That's the fraction. That tells you the percentage of the data that's explained by the line. And correlation and regression must be interpreted with caution. Plot the data to be sure the relationship is roughly linear and to find outliers. Don't let those outliers go bananas on you. So that's the section there on the chapter there. And you can see that I've covered most of the chapter in these little things here. So you can quickly look at these sections if you want, or just pay attention to the video that I'm trying to talk through. So you can see that I've skipped that, and for a reason, because again, the time that you spend on there is not important. The time is spent on finding the line that best fits your data. That's what the main point of this particular model is. Okay, now it's time for the assignment. So there are 4 problems, and these 4 problems are 537, 538, 550. But the 4th problem is one that I'm going to challenge you, because you may have to do this again for points. Did you get that? My voice is changing. Points. So I'm so excited that I love to say that word, points. So for this one, you're going to find a site or sites that have data, which you can plot a graph. That means you will have data from the explanatory variables and data that forms the response variables. Find the mean, find standard deviation, create a graph, and find the regression line, find the equation of the line, find the R-squared value, explain all your answers. So if there's only one problem that you can try to do, then do that and submit it on Brightspace. So I'm going to show you what I did for this particular one. And oops, that's over here. I wanted to see if there was a relationship between poverty levels, it's up here, and education ranking. Okay, so I went on this site here for poverty levels, and I copied the data, and it was kind of tricky, because you ended up, when you try to copy just the percentage, the poverty percentage here, like that, you end up with everything. So when you paste it on your chart, you get a whole mess. That's why this looks nuts. This still shows up, and I can't get rid of it, and I don't care. So this was from this particular site. These are the poverty levels, and I had to put them by alphabetical order. Okay, so it starts with Alabama going down. So that's where I found that. And then I wanted to see the education, the most and least educated states in America. So there's a certain type of way that they measured this, and they did a total score based on these variables up here. So they explained that. I'm not worried about that. I just wanted the total score, and you see Massachusetts has the highest educational total score. So I copied that, and it took a little bit of manipulation, and so I put it into this, and then I had to sort it by alphabetical order. So you can see that this is Alabama up here, and then the top one, Massachusetts, was down here, and that's its poverty level. So if you looked at Maine, Maine's poverty level is 11.2. That's as of 2023, I believe. And you want to make sure your years are the same. And then I copied and pasted. So if you look again at Maine, Maine's poverty rate is 11.2. Its ranking is 55.94, much lower than the Massachusetts 88.03. So then I did what I asked you to do, correlation. You should know how to do correlation between these two sets of variables. The mean of the poverty rate, this column C is the poverty rate, and then that's percentage, so it's 12%. The average poverty rate in the United States from these data is 12.5. Mean of the educational level is 51.2, so if you were doing the mean is above the average. Standard deviation poverty rate, that should be easy to do now, and standard deviation of educational level, so it's standard deviation of each of these two columns. And then I made a graph, so I highlighted just the data, making sure I had 50 pieces of data, one for each state, and then I made the graph, as you should know, and all these dots came out. Educational level, the label is educational level, and it's the percentage. That's the points, really probably the points, but I don't care right now. Poverty rate and percentage, so it goes from here to here. And then I added a line. You can see the line going through, the best line. My correlation is negative 0.8, so it's pretty strong, so it's a pretty strong line. My equation that I got out of here was a negative 4.256. That's my slope. Goes down, times x, that would be times educational level, and plus the y-intercept, 104.38. Great. R squared, this is good here. This is 0.6958. That means 70% of the points can be explained, but the line explains 70% of the points. That means only 30% are not explained. This line doesn't. So it's about a 70% line. So I could defend that. Again, because I have a strong correlation, it does not mean that education level is going to cause a poverty rate. In other words, the more education a state has, the lower the poverty rates. That's what this shows. The more education level you have, the lower the poverty rates. But that's not what we get here. So that's what the graph is showing. And that's what is part of this particular problem that I put here. So if you have questions about that particular one, it's probably the hardest one will be to find data. You can find sports data. If you're into sports, you can see if salaries will affect the team's wins. I even tried to do that, is to look at the, say, football. You look at their total budget for salaries and look at the number of wins they had for a particular season. Maybe if you pick like the last year's season, then you would see what each of the 32 teams that you have, what their salary is, and then see how many wins they got and see if there's a connection with wins and salary. Or you can do other types of comparison as well. If that doesn't work, then try one of these three problems if you can, at least one. Get in the habit of knowing how to do this and this and this and this and this. That's it for this long section. I told you I liked it, and it's almost an hour long, so hopefully you had a chance to snack and nap, or if you do both at the same time, to snap, or maybe this video will make you go and snap. But that's it for now. I'll be talking to you later. Take care.